Good afternoon / morning, everybody. Welcome to another TACO sponsored webinar. Today's webinar is on expansion tanks, sizing and selecting. My name is Brett Zerba, and I'll be the moderator for today's webinar. Rich Medairos, another TACO employee, will be the main presenter. Before we get started, let's go over a couple of ground rules, not ground rules, but introduction stuff. If you could wave your hands, some of you wave your hands that you can see Rich's screen, and I see some people, Mohammed and others, Jeremy, waving their hands. You can see Rich's screen, and I'm obviously you can hear me as well. So thank you for that. Also, there are 2 handouts available. So if you look in your little, listing of stuff over here, right up below the questions, above the questions, you can see some handouts. And these 2 handouts are instruction sheets associated with the CA, TACO CA expansion tank. And Rich will get into a little more details about those, the specific models and whatnot in a second. So there are some handouts. Feel free to download those. Again, questions. I'll be monitoring the questions and bringing them up periodically throughout the presentation. So feel free to type them in as you get a chance. And last but not least, if you okay, tomorrow, 24 hours after today's presentation, you'll receive an email, and in that email will be a link to the recording from today's presentation and a link to a PDH hour certificate. And if you are require professional development hours for your in the United States, well, I believe it's just the U.S. It could be other. Anyways, I know it is the U.S. anyways. And you can use that in your state. Feel free to download it and utilize that. And that's about it. TACO is a 100-year-old privately held company, started in 1920 by Elwood White. We are currently 3rd generation. It's privately held, so the same family has owned it. The White family has owned it since day one. The current owner is Johnny White. Hopefully some of you have met him or seen Johnny speak at different events. He's quite an individual. All of us employees love the guy. He's just a phenomenal person. And his senior management team is now led by Cheryl Merchant. Cheryl is we're actually a global privately held company, global president of all of TACO's operations, TACO Comfort Solutions operations worldwide. And her team have done a fantastic job this year, every year, but specifically this year, especially this year with the pandemic that we're all going through. So thank you, and our hats off to them. And the other thing Rich and I like to mention is our production folks. And I'm not sure many of them are hearing this, but some of you folks, I see some familiar names on here, have been to our facility, walked through the facility, and you know what a great staff we have out there producing our parts. And they have continued to produce a product through this whole 9 to 10 months. It's not 2 weeks anymore. It's not a 2-week shutdown anymore. It's 9 or 10 months. And hats off to that team and what they've been able to do. And others in the world, right? Other manufacturing companies have had the same issues, and I'm sure they're having some successes as well. So thank you. Hats off to those folks as well. Rich will give him an introduction on his expertise very, very shortly. And please ask questions. This is really, it's a great topic to get questions out there. We all can learn, and Rich and I continue to learn when we get questions from folks like yourself. So bring them up. And if you have a story about an expansion tank, and you can kind of type it in there, and I'll bring it up, and I'll try to paraphrase it so we can get that there. Successes or not a success. So it's an important component of a HVAC hydronic system. So I think I'm done yapping. So I am going to say, Rich Medairos, take it away.
Well, thanks, Brett, for that great introduction. My name is Rich Medairos, and I will be doing today's presentation. My background is I am a mechanical engineer. I specialize in the engineering design of HVAC systems. I am a PE, and I've been doing this for multiple years. So let's get right into our topic today of expansion tanks. And I have just a little agenda here to go over with you folks. We'll first talk about the type of expansion tank sizing, expansion tank selection, and location of expansion tanks, the questions at the end. By the way, you're welcome to type in questions at any time in the presentation, and then Brett will ask me to pause, and then he'll read the questions, and we'll try to answer them in real time for you. Okay, so types of expansion tanks. I do have a narrative initially, but we'll get right into some photographs, so don't worry so much about the narrative, but I do like to list them up front. So the first category is called a plain steel tank. The second category are bladder style tanks. And bladder style tanks come in two general formats. One is called a full acceptance bladder, which I'll define in more detail, and the other one is a partial acceptance bladder. And then the third category is called a diaphragm style tank, and they only come in partial acceptance. Okay, now that we've gone through the narrative list, let's take a look at some photographs and see what they actually look like. So the first tank that we're going to talk about is called a plain steel tank. Now, a plain steel tank is just as the name implies. It's just a metal pressurized container. In this case, it happens to be mounted horizontally. On the left-hand side is a couple of connections, and typically what's connected to those two guys is a sight glass, and allows the operator to determine the water level inside the tank. So if the sight glass shows the water level is here in the sight glass, then that would be the water level inside the steel container. There are two other connections at the bottom. One typically is connected to the system. Also, I'll just break the pipe here and show it connected to the system. And the other connection is typically connected to some kind of drain valve or blowdown valve. And that goes usually to a floor drain over here. And that's it. That's all there is to a plain steel tank. There's no bladder physically inside the tank. Essentially, it's just an empty container. Okay, so let's go on to the next category. Let's see if I can erase these lines here. The next category is called a bladder style tank, and the first one in the bladder style tank is called a full acceptance. And I have over here on the right, I have a cutaway of a bladder style tank. And if you'll notice, it's made up of two major components. There's the steel container. I'm pointing to that steel container on the right. That's the green device. And then physically inside the tank is the rubber bladder. Sometimes people refer to it as a balloon. And in terms of where the water and air goes, the water, when it expands, goes inside the bladder. And we do have to have air that we add to the void space. So I'm pointing to the void space now. That's the space between the bladder and the steel container. And that's where we add compressed air. Now, at the top of the tank, there's a little collar that protects the Schrader valve. And I have a picture of the Schrader valve over here on the left-hand side. It's exactly the same valve that you find in your car tires. May not actually have this mounting mechanism down here. But the valve itself is the same that you find in your car tires, basically. And that's where we can add compressed air. And when we add compressed air, we add it to the void space. And that's on the outside of the bladder and inside of the steel container. Now, when we ship expansion tanks from the factory, we pre-charge that air side, that's again, the void space, to 12 pounds per square inch gauge. 12 pounds per square inch. So we ship it from the factory, pre-charge pressure to 12 psig. All right. So now let's look at, oh, and one other thing. The reason we call it a full acceptance tank is because the physical volume of the bladder is the same as the physical volume of the steel container. So in our example here, if the steel container happened to be 200 gallons, that steel container, I'll just put a G in here, that's equal to the bladder volume. So the steel container and the bladder are the same. Hopefully I spelled that correctly, Brett. Spelling has never been one of my best attributes. So a full acceptance tank has a bladder whose volume is equal to the steel container volume. Okay, any questions floating out there, Brett, before I go on to the next type?
Well, we actually do have a basic question. Why is an expansion tank needed or so important in an HVAC hydronic system?
That's a great question. So fundamentally, when we have a closed pressurized fluid system, which typically say hot water or chilled water, that was not open to the atmosphere. And so when we heat up the water or fluid that's in those systems, the water expands. If there was no place for the water to expand, then you have a problem with equipment being destroyed. Since fluid water, in this case, for the most part, is non-compressible, it only takes a couple of degrees to create expansion. And if there's no place for the water to go, it would break something, either a pump, a pipe, or a piece of equipment along those lines. So the main purpose of an expansion tank is to allow water to have a place to expand when it heats up. The second reason is that it becomes the pressure control point in a system, and we'll talk about that in a little bit more detail. Any other questions, Brett?
Awesome.
Okay. The next category is called a partial acceptance tank, and just as the name implies, the bladder does not hold the same physical volume as the steel container. Again, in my cutaway version here, here's the steel container. And again, let's assume the steel container holds 200 gallons. And then you can see the bladder in this case is dramatically smaller than the one I showed you previously. And that bladder has less volume than the steel container. So if the bladder had less volume, for example, I don't know exactly what it would be. I'll show you with some examples later on in this discussion, but in terms of this picture right here, but let's just make an assumption and say that that bladder has a volume of 60 gallons. If the bladder volume is 60 gallons and the steel volume is 200 gallons, then we say it's partial acceptance. So partial acceptance means that the bladder has a smaller volume than the steel container. Okay. And then the next category, I could click on here. The next category is called a diaphragm style tank. And again, that is a partial acceptance tank. I may repeat what I said in the last discussion. In a partial acceptance tank, the steel container, again, perhaps could hold 200 gallons. But in a diaphragm style tank, since it's partial acceptance, it would also hold, rather less than the 200 gallons. And the other difference is that a diaphragm style tank doesn't really have a balloon per se or a bag per se. It's kind of a half of a bowl, or it looks like a bowl shaped rubber connected to the rubber container, connected to the inside circumference of the tank. And one of the major differences between diaphragm style tanks and the other style tanks is that the other style tanks in certain categories, not categories, but certain models can have, you can have the bladder can be replaced. So you can take the bladder out if it should fail for some reason and you could replace it. In a diaphragm style tank, it's not only partial acceptance, but the diaphragm cannot be replaced. If it should fail for some reason, you cannot repair the tank. We can't fix it. You have to dispose of the tank and purchase a new one. So those are the different style tanks. And by the way, in terms of adding air, this top part of the tank here is the air side. There's the collar that protects the Schrader valve. And the Schrader valve I showed you in the previous slide is the same thing. So that's where the air goes. The water connects to the bottom. Actually, you can see over here, let's say I put an imaginary pipe over here, connects to the bottom of the tank, and that's where the water goes over here. So there's the water for that particular tank. Okay, before we go on to sizing, any questions, Brett, floating out
Yeah,
there?
there's always this common question. I think it comes up every time we discuss expansion tanks. What's the advantage or reason you would install a partial or diaphragm over a full acceptance?
That's a great question. So let's go back. So the bladder style full acceptance tank with a serviceable bladder means you can physically replace it. That's the most expensive tank that you can get. The partial acceptance is a little bit less expensive, and the diaphragm is the least expensive. The diaphragm cannot be repaired. So if it should fail, you have to replace the whole tank. The partial acceptance, depending on the model, you can get a partial acceptance with a replaceable bladder, in which case, if the bladder should fail, you can replace it. And same thing holds true with this model, the full acceptance, you can replace the bladder. Now, one of the advantages of the full acceptance bladder style tank is that, like I said a moment ago, the volume of water that can be held by the bladder is equal to the metal container volume. So if for some reason the air side should leak out and the bladder fills up with water, the bladder would not rupture because it would be contained by the steel container. However, in a partial acceptance, if the bladder can only hold, say, 50 gallons and the steel container was 200 gallons, and someone let the air out, it filled up with water, it's possible to rupture the bladder. And the same thing holds true, by the way, in a partial acceptance. It's possible to rupture the bladder in a partial acceptance. So on a sliding scale, the first one I showed you is the most expensive, but it's also the most reliable and also it's serviceable. The partial acceptance can be serviceable, but you run the risk of rupturing the bladder if you should put more water in the bladder than what it can hold. And then the diaphragm style is the least expensive, but it's disposable. Once you destroy the diaphragm, you have to dispose of the tank. Hopefully that answered that question.
I'm sure it did. I mean, it's yeah, it's subjective to your own ways, you know, what you think. Price, really. There's another question that I don't see too often. Do you see any benefit to including a sight glass on the bladder tank?
Not really, no, because first of all, you could potentially put it inside. I would say no. There's no real benefit to putting a sight glass in there. So I'm going to go out on a limb and say no.
Okie doke.
So when it comes to expansion tank sizing, that's our next discussion here, then we have to account for 6 things, and I'll just run through the list. The minimum or fill pressure in pounds per square inch gauge, and this is the pressure at the expansion tank. The maximum pressure at the expansion tank, the minimum temperature of the system, the maximum temperature of the system, the fluid type, and finally, the system volume in gallons. Now, today's discussion is all going to be based on US units or imperial units. So let's talk a little bit about the sizing, and let's look at the following problem. Given a 75-foot tall office building, let's find the expansion tank size. Okay, so I have a little diagram of a 75-foot tall office building. And one of the things that I just want to emphasize is that the mechanical room is at the lowest part of the building. In our case, the mechanical room is on the first floor. So we have to keep that in mind when we do some of these calculations. All right. So let's make an assumption here, and let's assume that we have piping that goes from the lowest part of the building, let's say, and again, let's assume that it's along the floor here. It may not actually be in the real world, but in our example, let's say it goes along the floor. It goes all the way up to the highest part of the building. And then I'm going to put a little manual valve up here. And I'm going to put a plastic bucket at the top of the building. And I'll talk about that in a minute. I have a manual valve that I can open and close. And let's say that I have a fill station at the bottom of the building here. And let's say this pipe is capped for right now. And from that fill station, I have a valve. And that valve is a manual valve and allows me to add water to the system. So I'm going to open the valve from my fill station, fill this pipe with water all the way to the top, and then when I get 1 or 2 drops coming out of the end of the pipe, I'm going to close my fill valve down here, and I'm going to close my valve at the top of the building. Okay, so now my pipe is filled with water from the very top to the very bottom. So initially, and I'm going to ask you folks that are out there watching this presentation, get ready to type into the question area the answer to my following question, and we'll give you a couple of seconds to type in an answer. But under the circumstances that I just gave you, what would the actual pressure be if I had a pressure gauge at the top here? What would the pressure gauge read at the top? And while you're thinking about that, what would the pressure gauge read at the bottom? So Brett, while I'm chatting here, did anybody come up with an answer as to what the
lot of
pressure
zeros
would be?
already.
Okay,
Chris and
that's
Daniel
correct.
already said 0. Top.
The pressure at the top of the piping system would be 0 pounds per square inch gauge, PSIG. And the pressure
I have 32.46 PSIG and 75 feet. So it depends. I forgot what you said, PSIG. So anyways, that's for the bottom.
Yes, so the pressure at the bottom is simply the height of the building converted into pounds per square inch. And the conversion factor is 2.31. I'll write this up here, 2.31 feet, FT per PSI. And as someone just indicated, if the pressure is 75 feet of water column, I'll put that in here, 75 feet of water column converted into pounds per square inch, I would divide that 75 by 2.31, and the pressure at this gauge at the bottom would read, what did we say that was, Brett? 32 and approximately 32.5, I think is the number that someone said, and that's correct.
Yeah.
32.5 PSI.
You want another digit was 46, but 5 is good.
Yep. Yeah, I'm rounding it off to 32.5. Now, here comes the next question. We just said that the pressure at the top was 0 pounds, but we don't want 0 pounds at the top. We want something greater than that. And most people would say, look, I want a pressure at the top of the building somewhere between 5 and 10 pounds. So I'm going to kind of just put between 5 and 10. And the reason for that is I want to pressurize the piping system so that if I have an air vent at the top here, I have enough pressure to push the air out of the piping. I also want to have enough pressure at the top to avoid any cavitation that might occur if I had a pump or some other device. So for our example today, since I just said we want a pressure somewhere between 5 and 10, I'm going to make the arithmetic simple. I'm just going to put in 7.5 at the top of the building. And again, if someone wants to type in, if I add pressure so that I have 7.5 pounds at the top, what's my new pressure at the bottom of the building? 7.5 at the top.
40, Scott. Scott said it, and I guess said it as well, and Jean Luc. We've got a lot of 40s.
40, and it's simply 7.5 plus the 32.5. That's the pressure we said was the difference between the top and the bottom of the building. And that's equal to 40 PSI G.
And by the way, most of the folks typed in PSIG, so that was they're learning. That's good. Good crew.
That's excellent. Okay, so before we go on to the next screen, any questions about anything we did here? This is very important information, very, very fundamental, very straightforward.
No, sir.
Okay. Well, let's erase all this stuff and go to the next. In our mechanical room, this is what our piping is going to look like. We're going to have an air handling unit down there, expansion tank, our pump, fill station. So in a minute, we're going to talk about the minimum pressure that we need at the bottom of the building, and we actually just calculated that. We said the minimum pressure is the height of the building converted into pounds per square inch gauge. In our case, 75 feet divided by 2.31, and that's feet per PSIG equals 32.5 pounds. We want somewhere between 5 and 10 pounds at the top of the building. And for today's example, I wanted to do simple arithmetic, so I chose 7.5 pounds, halfway between 5 and 10. And if that's the case, then the pressure at the bottom of the building is going to be that 7.5 plus 32.5, and that's where the 40 PSIG came from, and that is the minimum pressure at the expansion tank. Okay, so we just decided what the minimum pressure is at the expansion tank, and I want to emphasize that, so I'm circling the minimum pressure. It's also known as the pre-charge pressure. Now, if you remember what I said earlier, the tank comes from the factory pre-charged to 12 pounds. In this system, the tank's pre-charge pressure has to be increased from 12 pounds to 40 pounds, and we have to do that before we physically connect the tank to the piping system. It's an extremely important step. So we've just calculated the pre-charge pressure. We've gotten the tank from the factory, and then we add compressed air through the Schrader valve to increase the pre-charge pressure to 40 PSIG before we connect it to the piping system. Extremely important concept. Okay. Now we've determined the minimum pressure or fill pressure. Let's go on and figure out the next thing, and that is the maximum pressure. So the maximum pressure is a little bit more involved, but it's fairly straightforward. In our example, this is one method for determining the maximum pressure at the expansion tank. There are other methods. They are all similar to this method, but we're going to use this one for today. We're going to assume for a moment that our maximum design pressure for our equipment at the lowest part of the building is 150 pounds per square inch gauge. And we have a pressure relief valve or safety relief valve. We want to make sure that the pressure does not reach the maximum design pressure. So we're going to set the relief valve at 10%, minus 10% of the equipment rating. So the equipment is 150 minus 10% or minus 15. So the pressure that we're going to set our safety relief valve is 135. Now, safety relief valves are a very simple device. Basically, it's a valve with a spring and a disc. And if you get close to the setting of the safety relief valve, they can drip or weep or leak a little bit. So we want the piping system that's connected to the safety relief valve to not have a pressure greater than 130 pounds. So I'm just making it 5 pounds less. I mean, you could make it 10 pounds less, but I'm making it 5 pounds. So it's 130 pounds at the piping system. Well, let's assume that the pump has the ability to add the delta P of 20 pounds in the system. So if I wanted to have a maximum in the piping system of 130, then I wanted my suction pressure to be 130 minus 20 if the pump delta P is 20. So my pressure on the suction side of the pump wants to be 110. And that's also the pressure I want to have for my maximum pressure for my expansion tank. And the reason that these are the same two numbers is because the expansion tank needs to be connected to the suction side of the pump. And that connection point is called the point of no pressure change. So just repeating, let me go backwards now. If I had 110 at the connection of the expansion tank, which is the maximum pressure of the expansion tank, the pump added 20, that would be 130. If I wanted the safety relief valve to be 5 pounds above that, I'd set it at 135, and that's 10% less than the maximum working pressure of my system. So I can erase all my handwriting right now, and I can just put in all of the values that we just talked about. So now I've determined not only my minimum pressure or fill pressure, but I've also determined my maximum pressure at the expansion tank.
Where did you? Yeah,
that?
there was a question. Where did you get the delta P for the pump?
So in this case, I had selected a pump, and the differential pressure at shutoff head, in other words, I happened to pick a pump that had a shutoff head of approximately 20 pounds. So I'm going to draw in an imaginary valve. If I put a valve here on my piping system, and I put a valve over here on my piping system, let's say they were manual valves, and someone closed each one of these valves, then the maximum pressure that my system would see would be equal to the suction pressure plus the shutoff head. So in other words, at zero flow, there's no place for the water to flow in my little example here. So the maximum pressure that the pump could produce is the shutoff head, and that's at 0 gallons per minute. And in this case, I happened to look up a pump that had a 20 PSI differential pressure at zero flow. So that's where I came up with that value.
Very important. That's not an arbitrary number. That is a findable number from the pump curves.
Correct. So anytime you have a pump, once you've made your pump selection and you're looking for the maximum pressure, you can easily look into the pump curve and you can see the shutoff head. Any other questions, Brett?
No, sir.
All right. So moving right along, as they say, we now know the minimum or fill pressure. We now know the maximum pressure at the expansion tank. The next thing we want to determine is what is the minimum fill temperature. And in this case, I happen to live in New England in the States, and our groundwater temperature is pretty constant at around 50 degrees Fahrenheit. So if I'm taking water from a well, I happen to have a well at my home, and I know that water temperature is around 50 degrees year round, and that would be the fill temperature of the system. And if it's a municipal water supply, that piping is underground, so it's also at 50 degrees Fahrenheit. Now, I know talking to folks from the Middle East, for example, they have groundwater temperatures that are substantially higher than that. They might have as high as 70 or 80 degrees. And I've talked to folks from Alaska, and they've told me that they have groundwater temperatures that are typically around 40 degrees Fahrenheit. So the initial or fill temperature is a function of the water supply that you have in your particular part of the world. And that would be the minimum temperature that you would have for filling your system. The maximum temperature would be based on the system design. In my case today, I'm using 180 degrees for my system design temperature. We need to know item number 5 is the fluid type. And for today's example, I'm using water with a specific gravity of 1.0. And the last thing we need to know is the system volume. And so I've estimated the system volume in my imaginary system to be approximately 2,000 gallons. So now I have all the 6 major categories for sizing an expansion tank. Now I can use that information in my expansion tank sizing app. So I'm going to go live to our website. Click on the website over here. So I'm now at the TACO website, the home page. Just to the right of center, you can see selection tools. You're going to click on that. And then on the left side of the page, you're going to see expansion tanks. It's going to take me into the expansion tank selection app. Now, if you'll notice, the units I said were US. In our case today, you have a choice between US and SI. Basically, SI is System International, and that would be metric system. Fluid, we're going to leave it at water for now. The piping material, I'm going to leave it at copper, and I'll show you our 2 choices are copper or steel, but I'm going to leave it at copper. The system volume is what we estimated, and we said that was 2,000 gallons. Let me zoom in a little so you can see. That's a little bit easier to read, right, Brett?
Yep.
So there's 2,000 gallons. The minimum or fill temperature in my case is 50 degrees. And again, that's dependent on where you are in the world. The maximum design temperature for my system is 180 degrees. Now I need to have the minimum or fill pressure at the expansion tank, and we calculated that, and we said that that was 40 pounds. And the maximum pressure we wanted at the expansion tank is 110. Now I've filled in all the data, and that's all I need for this app. And then I click on search. When I click on search, oops, let me erase this couple of little red lines here. The software has made several selections. So before I go into the actual selections, I want to point out a couple of quick things that the software has done. The software has looked up the specific volume of the fluid at the minimum and maximum temperatures. And between those two values, one there and one there, and the volume of the system, I should have scrolled down just a hair. There it is. With those two values and the volume of the system, the software has calculated how much the water will expand. And in this example, it'll expand approximately 53 gallons. So kind of keep that number in the back of your mind. If we were using a plain steel tank, we'd have to have a plain steel tank that had a minimum volume of approximately 354 gallons. We're going to skip over the plain steel tanks for a moment and focus most of our attention on the bladder style tanks. A bladder style tank would require a steel container volume of approximately 95 gallons. So let's look at what the software has selected. The software has said that, okay, in order to meet your design criteria, we're going to need an expansion tank whose steel volume container or tank container is 119 gallons. That's greater than the 95, so it meets that criteria. And in this particular case, the acceptance volume of the bladder is 119 gallons. Excuse me one second. Is 119 gallons for the bladder. Now, since the bladder volume is equal to the tank volume, then we say that this is a full acceptance tank. If you recall from my previous discussion, I said that whenever the bladder volume is equal to the tank volume, it's called a full acceptance. So the first selection the software has made meets the requirements, and the acceptance volume has to be greater than the expansion volume. In this case, that's approximately 53 gallons. So that first tank meets the criteria. Let's look at the second one. Again, we're looking for a steel container that's at least 95 gallons. This one's 112 gallons. In this case, the acceptance volume is 61 gallons. Well, it meets our criteria because we need one that's at least 53 roughly gallons. But in this case, the acceptance volume is less than the tank volume. So we can kind of say there's the tank volume. The tank volume is greater than the bladder. And so that's called a partial acceptance tank. Now I'm going to skip over the PAX for a moment and go to the fourth one down, which is the CX. And if you'll notice, the steel container tank is 57 gallons. Well, that's not enough. So, but over here we have the number 2. So if we multiply 57 times 2, that's going to be 114. And 114 is greater than 95, so it meets that criteria. We have to multiply the 27 times 2, that's 54. And 54 is greater than what's required by the expansion, and so that tank will do the job. Now, when we come to a plain steel tanks are typically not used in new designs today, although we have seen a couple here and there. Generally, they're part of the replacement market. Years ago, people used to use plain steel tanks. And if you'll notice, the plain steel tank over here on the left side has to have a minimum volume of 354 gallons, so the software selected this one. So you can see how much bigger the plain steel tank needs to be, almost 4 times bigger than the bladder style tank. And the main reason for that is you cannot pre-charge the plain steel tank. You have to start the tank at atmospheric pressure, and you have to add water to the tank until you get to the pressure that your initial fill pressure, in our case, was 40 pounds. So any questions about the selection and what partial acceptance and full acceptance, I know I'm repeating a little bit, but what all that means. Any other questions out there, Brett?
No, there's a question. Let me ask this one. I don't know where else to fit it in. If there is a leak in the piping system, will it be seen at the expansion tank pressure gauge, assuming there is no automatic makeup?
Yeah, that's an excellent question. So let assume for a moment that the system temperature has reached equilibrium and there's no more increase or decrease in the system temperature. If the fill valve is closed and there's a leak in the system, yes, the pressure will start going down at the expansion tank. But there's a lot of ifs in there.
Yeah.
Anything else?
No, you just there's always the question about just reiterate, why do you suggest putting the expansion tank as close to the suction of the pump as possible?
That's a great question. So let's go back to our little diagram that we looked at a few minutes ago. And let's go back here. So the reason that you connect the expansion tank to the suction side of the pump is because that's the point of no pressure change. So in our case, we start off with a minimum pressure of 40 pounds. That's our fill pressure, assuming for a moment that we have not started heating the system, which means that the water temperature is now still fixed at the fill temperature, in our case, 50 degrees Fahrenheit. When I start the pump, the pressure at the suction side of the pump will remain constant because it'll be the fill pressure in this case. The pump could be a variable speed pump. So the discharge pressure would be a function of the pressure differential across the pump. Well, if the pump is running at a very slow speed, the pump differential pressure, let's say, is just 3 pounds. I'll make up a number here. Well, if the fill pressure is 40 pounds, the discharge will be 3 pounds. Remember that the point of no pressure change is at the pump suction. Now, as the pump increases in speed, the pump suction pressure remains constant and the discharge pressure increases as a function of the pressure differential across the pump. Now, I do not recommend, we never want you to connect the expansion tank to the discharge side of the pump, but let's look at what happens. If I connected the expansion tank to the discharge side of the pump, that would be the point of no pressure change. Now, when the pump begins to, and let's assume for a moment that my pressure at the discharge side of the pump was initially, try that in English words, was initially set at 40 pounds, but someone had inadvertently connected it to the discharge side of the pump. Well, as the pump pressure differential increases, the discharge pressure remains constant because that's where it's connected to the expansion tank, but the suction pressure begins to drop. If the suction pressure drops low enough, you could have the pump cavitating. So one of the main responsibilities of the expansion tank is to ensure that you had a fixed minimum pressure at the pump suction in order to prevent the pump from cavitating. So hopefully that answered that question, Brett.
Yep, that was a great answer.
Okay, so let's continue along here. That's it, we want to go forward, not backwards. So we've got through all of the pressures and through the selection. Oh, and now I want to go back here and show you a couple of other quick things. So let's go back to the selection app, which I think is here. Yes, okay. All right, so one of the things that we want to mention is that what happens if you change the physical location of the expansion tank? Well, if I move the expansion tank and mechanical system, right now I have it on the first floor of the building. If I should move that up to the top floor of the building, assuming, and again, oversimplifying my diagram, my pressure at the top of the building, we said, was 7.5 pounds, so it's no longer 40 pounds. Now, keep in mind, the moment, if you make a mental note, that our tank size is 95 gallons and our expansion is 53 gallons. All right, so I'm going to change that fill pressure to 7.5 because we said that's what we want for minimum at the top of the building. And the maximum pressure at the top of the building would be 110 minus 32.5, which is equal to 77.5. And then I go down here and click on search. Now, if you'll notice, the expansion is still exactly the same. Because remember, the expansion is a function of the volume and the temperature difference. So the expansion is exactly the same, but look what happens to the tank. The tank gets physically smaller because of the pressures. So now I no longer need a steel container that's a minimum of 95 gallons. I only need a steel container of 70 gallons. And I no longer need to have the expansion or acceptance volume is still the same, but the tank physical volume is smaller. So whenever you move the expansion tank from the lowest part of the building to the highest part of the building, the expansion tank always gets smaller. So that's one of the consequences of moving the tank, changing its elevation. Okay, and one other thing I wanted to point out. Let's erase all this stuff. Let's go back to our original criteria of 40 pounds and 110 pounds. Going back to our original example. Now, let's assume for a moment that we have this project, and I've shown you the diagram, and the selection was based on water. Now, this happens periodically. We'll get a call at the office back in Cranston, and someone say, hey, look, I selected an expansion tank. I hooked it all up. I did everything I was supposed to do, but the safety relief valve keeps going off. Well, what's going on? What's wrong with your tank? And I'll say to them, okay, let's go through the selection process, and I'll walk them through what's on the screen right now. I said, now let's just reconfirm. Did you fill the system with water? And they said, no. It was always supposed to have propylene glycol in it at 50% concentration. I said, well, the selection was based on water. Let me show you what happens to your existing installation if you put in propylene glycol at 50% concentration. So I'm going to change the fluid from water to propylene glycol, change this to 50%, click on search. Now look what happens. The expansion, instead of being 53 gallons, is approximately 90 gallons, just over 90 gallons. And the tank would be required to be 160. Well, remember, you only have 119 gallons in there. And because the tank is physically smaller than what's required in this selection, then when the fluid heats up, it'll open the safety relief valve, and you'll have water, in this case, propylene glycol and water all over the place. So by simply changing, if you don't change any of the sizing, but you simply change the fluid characteristics, then you run into a situation where the tank is too small if you should put propylene glycol at 50%. Okay, so we've covered all the major items that we wanted to cover in this presentation. Do we have any other lingering questions out there, Brett?
Yeah, we need to go back. You need to, if you don't mind going back to your diagram, please. All right.
This diagram?
Yep. Okay, so previously we discussed the minimum pressure equals fill pressure equals pre-charge pressure.
Right.
But the diagram shows a city makeup water connection, which is pressurized. So how do we, or what do we spec as the fill pressure?
So in our example, the fill pressure has to be 40 psig, and that's done at the pressure reducing valve. Usually these PRVs are adjustable, and in this case, we would set the PRV. I haven't shown every single thing on this, but you could put a pressure gauge here, and when that pressure gauge now reads 40 pounds, you adjust the pressure relief valve, the pressure regulating valve until it reaches, in our case, 40 pounds. And then at that point, if the pressure drops below 40 pounds, it'll add water to it. If the pressure goes above 40 pounds, the valve will shut off.
Excellent. While you're on this drawing, I want to reiterate that this is one of the most common issues that Rich and I come up with and others in our industry with expansion tanks. Before that expansion tank is piped into the system, you need to properly pressurize it. Before, once you pipe it into the system, it's a pain in the you know what to properly pressurize that expansion tank.
Correct.
They can't
Always
interrupt. Yeah.
pre-charge the tank to the calculated minimum or fill pressure before you connect it to the system.
A couple other great questions. What happens if you oversize the expansion tank?
So oversizing an expansion tank has no negative effect on the operating characteristics of the system. The penalty for oversizing the tank would be physical size, how much space it takes up, and cost. But if I put a tank in that's twice the size of what I need, in our example, we said we needed a tank that's roughly 100 gallons and an acceptance volume of roughly 53 gallons. If I put in a tank that's twice that size, then the maximum pressure obtained by the system will be less than 110 pounds, so that won't affect the system operating characteristics. However, the tank would be twice as big. It would consume more real estate and it would cost more money. So the only downside is that it's physically larger and costs more money. There's no negative effect to the system.
Excellent. Actually, the same person asked this question. What's the effect if you put in a too small of an expansion tank or potential problem? I think I already know the answer to that one.
So here's what happens. If the tank is too physically small, then in our example right here, what would happen is that the pressure, as the temperature of the system goes from 50 degrees to 180 degrees, the water would expand. There'd be less place for the water to expand into, and so it would reach the maximum pressure halfway through. I'm just going to say halfway through. It would reach the maximum pressure that we designed the system for during the expansion process. So before it gets to the maximum temperature, it would exceed 110 pounds. If it exceeded 110 pounds by a few pounds, it would set off the safety relief valve. So you get water all over your mechanical room if you didn't pipe the safety relief valve to a drain. That actually happened to one of our customers. They didn't pipe it to the drain, safety relief valve went off, and it flooded the mechanical room. It was a real mess.
Yeah, we have a couple of questions pertaining to chilled water systems. So you did a hot water system. Are the calculations the same pretty much in the methods that you did for a chilled water system and locating the expansion tank?
Yes, so for chilled water and the hot water, everything is the same except for the temperatures that you choose. So when I'm designing a chilled water system, I pick the same fill temperature of around 50 degrees Fahrenheit, only I pick in this case a maximum temperature. Even though the chiller might be set at a maximum temperature of 55, I would pick a maximum temperature of around 110 degrees. And the reasoning behind that is simple. Some project gets built, and let's say we happen to be in New England, or let's take the Middle East, for example. So let's say the project gets built and the system gets filled, but the startup of the chillers is not going to take place right away. Well, your temperatures out in the Middle East could be very, very high. So you could have an empty building sitting with water inside the piping system, and the ambient temperature could get up to, say, 100, 110 degrees, in which case, as long as the chiller is not running, the water would expand to that new ambient temperature and eventually would set off the relief valve if you didn't pick a high enough temperature. So for New England, I pick 110 as my maximum temperature in case the building is sitting idle during the hottest part of the year. In other parts of the world where you have very, very high temperatures, you might go to 120 for your maximum temperature or even higher than that. That's the logic behind the chilled water system.
One more question, my friend. Does anything change if I have to use two expansion tanks? And can I use two expansion tanks? And does anything change? Would both come? Would I have to do the pre-charge for both the same?
Yes, that's correct. So everything remains the same. And so whatever you do to one tank, if you decided to put two tanks at half the size, each tank would get pre-charged, in our case, to 40 pounds. You would pre-charge it before you connected it to the system, but you could use two tanks in lieu of one. And that's typically that happens if you have a very, very large system, and it's not practical to put in a single size tank. You want to put in multiple tanks.
Actually, we snuck another question in here. So if I have a 10-story building, would it make sense, even if my mechanical room's on the basement, to put my expansion tank way up on the roof or a penthouse or something?
Well, it is possible to put the expansion tank at the top of the building if the mechanical room is at the bottom of the building. However, we would recommend that you run a dedicated line from the expansion tank down to the suction side of the pump that's at the bottom of the building. Now, that may not be practical, especially in terms of the height of the building. So another way of getting around that is that if you design a piping system that has, say, a single return from the highest point of the building down to the bottom of the building, and that return piping is sized so that the pressure drop at full design flow is negligible, then the return pipe acts like a dedicated pipe to the suction side of the pump. Now, that requires a substantial amount of design modification and calculations. So the simplest thing to do is to run a dedicated line. But yes, you can put the tank at the top and the mechanical room at the bottom.
So, we at the beginning I had said if folks had a story about expansion tanks to pop it in. So here's one here. We had an expansion tank collapse the neck like a vacuum. Huh? That's different.
Yeah, I'm not sure what's going on there.
Yeah.
So I don't have a good answer. I don't know what part of the tank they're talking about.
Yeah.
Can you repeat that again, Brett?
I know. I'm going to read it verbatim. We
Okay.
had an expansion tank collapse the neck like a vacuum.
Well, that's interesting.
Yeah.
Yeah, I'd have to chat with the folks that wrote that question and find out a little bit more detail of what exactly was going on. So yeah, I don't have a good answer for that one.
Well, you are done answering questions.
Well, I want to take this moment to thank everyone for participating in today's discussion. And I'm going to turn it over to Brett to say goodbye. So stay safe out there and take care. Bye-bye now.
Thanks, Rich. Great job. And thank you, audience, for all your great questions. The more questions, the better we all learn. And it really is very helpful. So thank you for being so interactive. And just a friendly reminder, there are 2 handouts. So hopefully you got a chance to download the handouts. They're instruction sheets, and they're available on our website if you didn't get to get them. So, but the more we do these presentations, the more I realize how important these instruction sheets are, and they really have a lot of valuable information in there. One of the folks asked a question about installing them horizontally or vertically, or vertically or horizontally, and the instruction sheets they actually say you can install them horizontally. I was so anyways. And someone just popped in a question: is the expansion tank sizer on your website? The app for expansion tank sizing is available on our website. Yes,
yeah, let me. We have half a second left. Let me just repeat how you access that.
Yeah.
So I'm going to go to click on tacocomfort.com, and just to the right of center, you can see this button that says Selection Tools. It's an online app. Click on that, and then on the left-hand side, third line down rather. Fourth line down is expansion tank. You click on that, takes you right to our expansion tank app. So yes, it's on our website, and it is an online app, and it's readily available. There's no cost or anything. You can
When
use
you
it
say
immediately.
app, you can app it onto your phone if you like.
Yes, it's available through the phone app too.
Whatever. So again, great questions. Read the instruction sheets. There's really a wealth of knowledge in there. And thank you so much. Be on the alert for the email tomorrow with access to a PDH hour credit if you need it. Make sure you can use it for your state, and a recording of today's presentation. But we don't hand out the slides, so you would need to download the presentation on the recording if you want it. But other than that, and getting a lot of thank yous, so thank you, Rich. Thank you, everybody. We do appreciate it. And to my friend Jerry out there, not sure, we ended up changing the bladder out. Maybe someone let all the air, the pre-charge air out of there. I don't know. That could be it. Anyways, stay safe out there. Oh, we have another Take-O Tuesday coming up. Go to our website and you can see it. I think the commercial one is early in the month of November. Flipping November already. God's sakes, November 20. Well, to be quite honest, I wish this 2020 would get over real quick anyways, to say the least. But yes, November 12th, we have Introduction to HSS Software, I believe. I could be, maybe that's wrong. Anyways, go to the website. I thought that's what oh, it's Tuesday. I'm sorry, Tuesday, November 10th. Tuesday, November 10th. Introduction to the HSS software. So stay safe out there. Thank you, everybody. We do appreciate it, and thank you for all the thank yous. Well deserved. Rich does a heck of a job. So goodbye, everybody.